Okay, so taking a look at other complex circuits, complex being that we're asking about what's happening in each individual circuit component instead of looking at the circuit as a total. So here we go. I've got another question. 3 small lamps are connected to an 18-volt battery, as shown. There's a figure there, a picture with some light bulbs and a battery. Kind of a circuit schematic. That's not actually bad, but it's kind of realistic. Assume the battery is ideal, has no internal resistance, and given in the figure. In short, in the other video, I talked about internal resistances. In real life, batteries actually have effectively little tiny resistors built into them. Now, it's actually as a function of how batteries are built that that resistance is there, but it's also kind of a good thing. One of the things that I'll bring up is batteries have a lot of energy, and you don't want all of that energy to be released in 1 second, just all at once, because that would be bad. That's a whole lot of energy. That would be, well, literally explosive. That's way too much. So it helps to have kind of something in there that will help throttle what they do. That being said, it's still dangerous to simply short a battery. Please do not do that. All right. This one, however, has no internal resistance. It's going to be an ideal battery, like the ones we've been looking at in class. They also mentioned that unlike most real bulbs, the resistances of the bulbs do not vary. I want you to think back to that lab that we did in class where we adjusted the potential across both a resistor, and we got a nice straight line for our resistance, and we did the light bulb, and it would curve a little bit more. It didn't perfectly follow it. That's more or less what they're talking about here. That being said, we ignore that promptly when we start working with things, and we treat light bulbs as perfect resistors, even though technically they're not. All right. All of the little asterisks out of the way and the small print done. Let's take a look at this. So we've got a circuit that looks something like this. I'm not going to draw the realistic looking diagram. I'm going to use what we've done in class. I've got a battery that then comes over to 1 bulb that is in series with 2 others that are in parallel. Now, this may not necessarily, in fact, this won't look like what you're looking at on your homework, but part of what I want you all to understand is how to deal with these realistically. There's also a switch in here. I guess I might as well include that in my circuit diagram. There we go. All right. I'm going to fill in some of the values I've got. So this first resistor, they mark for me as 3.2 ohm. This resistor is 2.8 ohm. And this resistor is 4.7 ohm. Great. Final thing that I know is that this ideal battery has a potential difference of 18 volts. First question, what is the equivalent resistance of this circuit? Okay, well, you can do this without doing the table, but since we're working on this, let's go ahead and take a look at our table. So, table, we've got total, we've got the first resistor, which I'll call A, we've got the second, and the third, which I will call B and C, respectively. R equals I delta V. Okay, let's see if I can refrain from writing down the wrong potential difference on the battery this time. 18 volts. I hope. Yes. All right. We don't know any of those values, at least for right now. We do know the resistance of A. First one that I come across, I call A, because I'm lazy, 3.2 ohms. Okay. B is 2.8, and then C is 4.7. 2.8, 4.7. Great. All right. They want to know what the equivalent resistance is. Well, that was something that we've worked on even in the previous section. So we are going to take the smallest section, which is this, and we're going to replace it with an equivalent resistance. It'll look a little something like this. REQ for this first step. I want REQ, these are in parallel, so 1 over my equivalent resistance is 1 over 2.8 ohms, plus 1 over 4.7 ohms. Now I know up to this point I've been trying to add things with the actual adding fractions. Today I'm going to be a little lazy. 1 divided by 2.8 plus 1 divided by 4.7. That gives me 0.569991. Fine. 1 over ohms. This is not my equivalent resistance. It is indeed 1 over my equivalent resistance. So I need to do 1 divided by this so I can get my equivalent resistance. My equivalent resistance is 1.755 ohms. Never forget that last step of inverting it. All right, so 1.755 ohms. That's the equivalent resistance of our parallel path. And this one is 3.2 ohms. These are in series with one another, so plus 3.2, we end up with 4.955. 4.955 ohms. On a regular day, I would probably call this 4.96 or maybe even just 5 ohms, but it doesn't hurt to keep a few extra significant figures because that's more or less how this particular system actually works. You want to be within 1% of your answer. The answer I have listed is 4.955. There we go. That's the correct answer. So we're good on that. All right, so to my knowledge, there's actually multiple parts to this. All right, we've got this. I have a good idea of where this is going next, and this is why the table approach helps out, because I filled this in, because the next question is, what is the total current of this circuit? They're looking for I, total. We'll look at that. We don't have to set much else up. We know Ohm's law applies right here, so I'm going to take 18 divided by that mess that we just found, 4.955. I get something like 3.63 amp. Didn't even have to write anything else. It's all right there for me. And the correct answer is 3.63 amps. Great. Next question. What is the current in the 2.8 ohm bulb? Okay, let's go back. They want to know what the current is in this one. And I presume another question is going to be about this one or maybe the other one, which means we're going to have to start getting creative. But again, here's where the table helps us out. If this is the total current, it's 3.63, that's what's coming out of the battery and going into the battery. But it is also what goes through the 3.2 bulb. 3.63 amps. With this, I can now solve for the potential drop across resistor A. 3.2 times 3.63, 3.63-ish. We end up with something like 11.63 volts. Now we need to do a little bit of loop rule. Plus 18 minus 11.63, and our potential drop across the 2.8 bulb is going to be the difference on that. So 18 minus what I just got here. I'm just leaving this in my calculator, not actually rounding it, but it should come up to something like 6.375 volts. Also, as a side note, you can go around the other path. You'll find that this is also 6.375 volts. All right, so I'm going to take this, and I'm going to divide it by 2.8. I find that 2.277 goes this way, and let's see, 2.8 divided by 4.7. I should get something like 1.356 going this way. 1.356 plus 2.277 gives me 3.63, which is what we had there. Junction rule is also supported. I probably did some extra work by filling in the whole thing, but I knew that I needed to find the potential difference across this so I could do loop rule and find out what's going on here. At least that's the main way that I teach you all in class, and by my consideration, probably the simplest of the ways. But they asked what the current is in bulb 2.8. 2.2766, so 2.277 rounded to 4 significant figures. That's the correct answer. And then the final question is, yeah, I did too much work. What is the potential difference across the 3.2 ohm bulb? Here we go. We already found that, as at least the way I directed you to. Part of finding the answer to the question before is actually 11.63, and they have the answer listed as 11.625, which would round to 11.63. So there you go. Once again, the table helps make this much more navigable, or whatever the word is. Words are hard.